Today I am going to talk about prospects of probing inflationary signatures with redshifted 21 centimeter signals. So we have heard a lot of talks about inflation and its signatures. Also we have heard some very good talks about redshifted 21 centimeter signal. So my purpose of this talk is to connect the two. I am going to talk about how to probe the inflationary signatures, particularly using the redshifted 21 centimeter signal. So I have done this work with my collaborators. So let me begin. So the primordial features that are mentioned in my title are basically coming from the inflationary era. So some of the inflationary models predict certain observational signatures which are known as primordial features. And because inflation also gives us explanation about the origin of primordial density fluctuations, they can leave their imprints in different cosmological observations such as cosmic microwave background and in the late universe as in terms of matter power spectrum. Also, thanks to the abundant neutral hydrogen, we can also observe its signatures in the neutral hydrogen distribution using the redshifted 21 centimeter signal, which is going to be the main highlight of today's talk. Okay, so there are several classes of primordial features, as you might have already know. I am going to focus on a particular class of primordial features, which is shown like this. These are bump-like primordial features. It can be predicted from a various class of scenarios, but the scenarios that I am talking about is particularly the particle production mechanism during inflation, where inflaton field couples with another scalar field and gives rise to burst of particle production during inflation, and that results in a bump-like feature. Since I am interested in the observational imprints of such feature, I will focus on its observation in different times of the universe. So such bump-like features can be parameterized by mainly two parameters. One is the amplitude, denoted as A1, and then the location of the feature in the co-moving wave number scale, which I am calling as K peak. So this black line is a usual scale invariant power spectrum, and in addition to that we have another component which is given by this primordial features. Okay, so throughout the talk I will be referring to these two parameters. So yeah, such classes of primordial features are discussed in various from various theoretical motivations. You can see these references. Okay, coming to the observables. So from the early universe we have certain constraint using CMB observations. So what I am plotting here is amplitude of the feature versus the location of the feature, and this is the different co-moving wave number scales. So from CMB observations have provided very good constraints on different varieties of primordial features, and we have obtained upper bounds on the amplitude of primordial features at different scales. So anything below this are consistent with the data, and anything above are ruled out by CMB observations. But this CMB observations as well as late time universe, we have some observations from matter power spectrum, and that gives certain constraints on slightly higher co-moving wave numbers region, but still all these comprise up to certain, or it gives access up to certain wave number range, but beyond this wave number range we do not have constraints yet. So this is expected to fill by the intermediate universe, which can be probed using the redshifted 21 centimeter signal. Okay, so from here onwards I am going to focus on only redshifted 21 centimeter signal. So in earlier talks we have heard about how to quantify redshifted 21 centimeter signal. Basically this is the differential brightness temperature, which is spatially fluctuating quantity. Also it depends on the redshift, and it depends on several factors. So the important factors that I am going to talk about are the baryon density perturbation, the neutral fraction of hydrogen, and spin temperature. All these quantities are spatially fluctuating as well as they have a redshift dependence. Now if you simulate the redshifted 21 centimeter signal, so this is how the light cone looks like. Here the color indicates the differential brightness temperature, and this is the time axis. So from early universe to the late universe up to 1 billion years, this is how the redshifted 21 centimeter signal evolves with time. Now once we know that this is the kind of signal that we are expecting, we can apply several statistics on this and to compare our model prediction with the data. So the simplest statistic that you can think of is take the average of the signal across various time. So that is what we call as globally average 21 centimeter signal, or global 21 centimeter signal in short. So this is the average 21 centimeter signal across redshift or across the frequency. So the dip and the peak of the signal gives valuable information about different stages of dark ages and reionization. I'll come to this in a minute. And the second thing that we can do is, since we have spatial fluctuations across each redshift, we can calculate the 2-point correlation function and construct 21 centimeter power spectrum. So you can do that at multiple redshift. So here we have information about the spatial fluctuation as well as the redshift. In global 21 centimeter signal, we don't have the information about the spatial fluctuation because we are averaging it out. And then we can also construct something called as morphological statistics. So these are the four Minkowski functionals calculated for a 3D field. I'll focus on the first two. This was discussed in Kandan-Weirkat's poster. So apart from this, you can also construct bispectrum and calculate its non-Gaussianity using different statistics. So now the question is, if I introduce primordial features, what are the expected effects on these different statistics? So this is the this was our previous work on how the primordial features affect average quantities like the average neutral fraction of hydrogen and average brightness temperature. So the evolution of average neutral fraction of hydrogen gives information about the reionization history. So 1 means completely neutral, 0 means completely ionized, and this is the global signal that I showed earlier. So you can see that from top to bottom, as we change the value of K peak, which is the peak location of the primordial features, you can see that there is shift of the global signal. Also there is a change in depth of the signal, also the width of the signal. So one interesting thing to see here is that there is a particular scale above which, if you increase the amplitude, it is shifting towards the low redshift, and after that scale, if you increase the amplitude, it is shifting towards the high redshift. And there is a particular scale at which the effect almost vanishes. I'll come to the reason in a minute. So this scale, we are calling this scale as a turnover scale because you can see a turnover of behavior. Similarly, in case of ionization history also. So this can be explained with the help of halo mass function, because the halo mass function gives common number densities of halos in a particular mass range. This is the halo mass function shown for a particular redshift, and here there are multiple curves, and the color of the curve corresponds to the location, peak location. You can see that since the halo mass function affects the number density of the halos, because halo mass function depends on the power spectrum, so you can explain this behavior by the halo mass function. So at particular, for example, this 0.5 megaparsec, the contribution at around this mass range becomes equal to fiducial model. That is why we don't see any effect in the global signal. Now, we also know that there are a lot of uncertainties in the astrophysical parameters. So if we change this, here I am showing 3 important parameters: ionizing efficiency, virial temperature, and the X-ray luminosity. If we change these parameters also, we expect to see several variation in the global signal. Now the question is how to distinguish this effect from the effect of primordial features. Now we can quantify this signal using different ways, which we have shown in the paper. Here I am just showing one method. For example, you can take the 3 important temperature and frequency range and plot it and see with variation of each of the parameter how the trend looks like. And it turns out that the variation of T virial has the same trend as the variation of the bump-like features. So it shows that there is a degeneracy expected with the virial temperature of the halos. And since it affects the ionization history, using the optical depth reionization parameter, we can put certain constraints on the amplitude of the feature. These are the current available constraints. I will move to the next one, which is 21 centimeter power spectrum. So this is the fiducial model, how the power spectrum looks like. This is K and this is redshift. The color indicates the value of 21 centimeter power spectrum. Now if you introduce primordial feature at this particular scale 0.4 here, you can see that visually you can, with the help of color, you can see that there is some excess of power. If you change the value of K peak, you can also see that there is a overall change in the power spectrum. So with analyzing power spectrum, you can definitely access more information about how the primordial features are affecting different scales and different redshift. You can quantify it using one-dimensional power spectrum. At particular scale, you can see how the evolution looks like. And then, then we also worked on whether the future instruments can detect such primordial features or not. So for that, we constructed a mock power spectrum using the SK low sensitivity, and we started with the input values we gave certain input values, constructed mock power spectrum, and with SK sensitivity, we wanted to see whether such input values can be recovered from SK. For that, we did an Bayesian MCMC analysis. So this was our previous result, 2023 results for certain SK-low configuration. And here these two parameters are the reionization parameters, ionizing efficiency and virial temperature, and the other two are the parameters for bump-like. So you can see that for these two parameters, pretty broad. Then because the SK lab had revised its antenna layouts, we redid this analysis. This is a new layout. Here what I've shown is the antenna position for two layouts. One is called AA star, which is shown by the blue dots, and the red ones are AA4. AA star will be coming up first. So with this new SK AA star sensitivity, after analyzing the after doing this same exercise, what we have found is 3 of the parameters were recovered within 68% uncertainty except zeta, which was slightly outside the 68% uncertainty limits. So the takeaway points are studying the primordial features are important both from theoretical as well as observational point of view. And primordial features can affect 21 centimeter signal because basically it is affecting the density fluctuations, and because the power spectrum is getting modified, it is also affecting the Halo mass function. That is why it is also affecting all other spatially fluctuating quantities like ionization fraction and spin temperature. And so we have seen the effect in globally average signal, power spectrum, and ecological statistic. Therefore, my argument is that restricted 21 centimeter signal can be used as a promising probe of inflation in near future. However, there are degeneracy with astrophysical parameters, so this is something we are looking into, quantifying the degeneracy and looking at certain redshift and scales where the effect of primordial features are unique. So our preliminary analysis shows that SK A star shows promising potential to probe the primordial